So our solution is called Phio TX, and this is about enabling this rapid adoption and monitoring and management of post-quantum cryptography. So let's talk about kind of how things work today and how an architectural change is needed in addition to the algorithms in order to protect ourselves. So at the bottom of the slide here, we have the two entities, orange entities, Alice and Bob. And the way that they work is Alice and Bob want to communicate. Alice says to Bob, let's do TLS 1.2 with a RSA 2048 key. Bob sends over his certificate and his public key. Alice takes that, generates a symmetric key, wraps it and encrypts it in Bob's public key, and sends it back. And hopefully, only Bob has access to his private key. If anyone else has it, they can steal the key that was negotiated, so that's a challenge. But now let's assume that only he has it. Now they have a symmetric key, and the symmetric key is what's used to encrypt the data. The public-private key pair is only ever used to negotiate the symmetric key. That's really important to understand. But the net effect is that Alice and Bob are basically negotiating the key and then sending the data over the same connection. And this is an architecture from 1976, back when Diffie-Hellman was created. There was no IP networking and routing, and the internet didn't exist. And so you negotiated the key and the data together because you only had one session. So let's take this architecture and now just plug in a new algorithm like ML-Chem. Well, what happens if that algorithm is broken? Well, I'm still negotiating the key and the data over the same session between Alice and Bob, and so the harvest now, decrypt later attack would still work in that instance. And so we're not really protected if we just change the algorithm. And so this is where we need to start thinking about a new architecture for this security element of key generation and delivery. And that's where Phio TX comes in. Phio TX is basically the blue boxes at the top, and it's similar in architecture design to identity and access management. Back in the day, we used to have usernames, passwords, and roles as data elements in every application. At some point, that became unmanageable, and we started to build things like single sign-on and then identity and access management. And once we did that, it became really easy to do things like have a global password policy for all applications and change it on the fly and not make any application changes, or snap in multi-factor authentication and not have to change or make any changes at all to my applications or how they operated, because the application just wants who's the user and what's their role, right? So the same idea here for cryptography is if I can do that and manage my post-quantum cryptography in this service level, I can now make changes without having to change my applications. And so what happens now is Alice wants a key and she wants it to be shared with Bob. But instead of doing it directly, she calls to her Phio TX key provider and says, I need a key of 256 bits and I need it to go to Bob. What happens is the Phio TX generates in memory only public-private key pairs for one or more, because we can do more than one algorithm at a time, post-quantum algorithms. And now the private keys stay with Alice in memory only, and the public keys go over to Bob, where he takes them and then he uses the standard key encapsulation method to generate a key and ciphertext. The key is not deterministic. So he doesn't generate a key and then encrypt it. As part of the process, he gets a key and the ciphertext. The ciphertext is sent back to Alice because only she has the private key, only she can decrypt it, and now they each have a session key at both ends, a symmetric key that they hand off, and now the Bob and Alice can use those two keys to communicate. So what have we done? Well, the first thing is we broke man in the middle, because it would at a minimum have to be man in the middles, right? There's two different sessions that are used for key establishment and data transmission. So that's a really big difference. The other thing we've done is we've gotten rid of this static pre-shared or private key on the device. You know, in the case of Bob, if his private key is stolen, all the data is compromised, even in a harvest now, decrypt later scenario. In this case, there is no static key ever that is used or can be used to decrypt keys or steal keys in the future, because they only live for as long as the key generation process is required, and then they're deleted. So it's really, really important to understand that this takes away not only man in the middle, but the threat from stolen, static, private, or pre-shared keys on the device, which is a big problem today that really needed to be addressed. And it's done because we have an architecture that permits it. The other thing you can do here is you can change an algorithm on the fly. So I can change the algorithm used at the key distribution level, and Alice and Bob don't care. They just want a symmetric key. Just like I can snap in two-factor auth into my IAM system, The app doesn't care how the user is authenticated, how strong their token is, or any of that. They just want to know who's the user and what's their role. In this case, Alice and Bob just want a symmetric key with an ID that they can share and make sure is, coordinated, and that's all they worry about. And so now when you think about changing algorithms in the future, this becomes really easy because I can make changes on the key distribution network and not touch any of my applications. In fact, you can do it with zero downtime, which is something that is really unique in this architecture. So when the keys are delivered, everything is zeroized from memory. All the keys are taken out, and we guarantee things like a key can only be delivered once. There's other guarantees on the security of the solution. Basically, once you plug this in, you're going to be much more secure, even if you were just using classical encryption all the way around.